Hello everyone, this is the fourth lecture of week 5. Recall that we were learning about Newton's method. So, in the previous 3 lectures we learned the general form of Newton's algorithm, argued that this method is has a faster convergence than the methods discussed before this, which is the other methods have linear convergence while Newton's method have quadratic convergence, right. So, we also showed this at the end of the previous lecture, and other than this we also mentioned 3 issues. One is no global convergence, there is only local convergence. Local convergence was also proved in at the end of previous lecture, and so the direction that we consider may not be a descent direction if the Hessian is not positive definite, and the other issue was regarding the inversion of the Hessian matrix, right. So, and we saw a lot of examples citing where those issues come from, right. So, in this lecture we will start looking at ways of getting around these issues that we just mentioned, right. So, yeah, we do not have global convergence, but can we twist the algorithm a little bit to get global convergence, right. So, yeah, I mean that is something that we can think about, and similarly the other issues. So, yeah, we may not have Hk to be positive definite, or yeah we inversion issues will be there. So, we will come to that, but I mean, is there a small tweak that we can do to the algorithm so that we actually I mean nullify these issues and get on track. So, that is what we will be discussing in this lecture. Okay. So, yeah, let me actually recall to you that okay, this is the last page. Yeah, so these are the issues: no global convergence, and yeah, minus Hk inverse Gk need not be a descent direction, and yeah, matrix inversion is a computationally expensive process. So, we will first consider this global convergence issues. Okay. I am going to introduce to you a method called as damped Newton's method. Okay. So, as I said, this is a small tweak of the Newton's method that we all know. Okay. So, what is damped Newton's method? So, I will just write down the algorithm. It is not it is exactly Newton's method except a change for one of the lines. Okay. So, yeah, first initialize as usual x naught tolerance and k equal to 0, and while norm Gk greater than tolerance, what are we going to do? The first step is, yeah, so fix dk equals minus Hk inverse Gk. So, this is fine, but now I mean in Newton's method you would just use alpha k equal to 1, right. So, here that is not what you are going to do. You are going to choose alpha k by backtracking line search. Okay. The rest is the same. Xk plus 1 is xk plus alpha k dk and k equal to k plus 1. Finally, output x star equal to xk. Okay. So, the only difference between Newton's method and damped Newton's method is that you choose alpha k by backtracking line search in the damped Newton's method, and in Newton's method you blindly choose alpha k equal to 1. Okay. So, I claim that this would actually give us global convergence. Okay. So, let us verify it for the example where we actually had the issue of no global convergence, right. So, if you go back, so you can see that this was the example that we considered, right. Square root of x 1 squared plus 1 plus square root of x 2 squared plus 1 as the example where there was no global convergence. So, if you had x naught equal to half comma half, you had convergence. If you had 1 comma 1, it was shuttling between 1 comma 1 and minus 1 comma 1 repeatedly, and when you had 2 comma 2, it blew up to infinity, right. So, we will use damped Newton's method to see if the issue is rectified or not. Okay. So, yeah, so this was the example for no global convergence, square root of x naught squared plus x 1 squared, and yeah, everything else is ready. So, we will just remove this k not equal to 100 business, and instead of so we will write d as minus h inverse g, and the routine for, we will copy this down instead of rewriting it. Yes, so here is it. Yes, all right, I think this is fine. So, yeah, we just write alpha equal to 1, and while Army-Host condition is not satisfied, you keep shrinking alpha by a factor of rho. So, you also have to write C 1 and rho. C 1, let us say it is 0.75 and rho is 0.8. Okay. And yeah, so this has to be x equal to x plus alpha into d. Okay. So, nothing else, everything is the same. So, and yeah, so you can see that for 2 comma 2, when we ran the Newton's method, we got infinity in 6 steps. So, let us see what happens here. Yeah, so in 3 steps you can see that you are at 0 comma 0, which is the right answer. So, we will give a bigger number, say 20 comma 20, to see if that is also taken care of by this particular algorithm. Yes, fortunately. So, you can see that in 4 steps you actually converge to 0. So, what this means is that if you choose damped Newton's algorithm instead of Newton's algorithm, yeah, it slows down a bit, that is correct, okay, because you are not having alpha equal to 1, right. So, that means your the step size is being pulled down, okay. So, but by doing that, damped Newton's method actually achieves global convergence, okay. So, I mean, to understand this physically, okay, suppose you have someone who actually runs very fast to the destination when you give him the direction, and what he does is, I mean, he sometimes oversteps, okay. So, then what do? You try to pull his speed down, saying that go slow, go slow, go slow, right. So, that is exactly what damped Newton's method does. Newton's method is going too fast. So, what damped Newton's method does is it damps the speed of Newton's method in each of the step. So, it uses a step size, so that it takes care of the fact that this does not overstep at each of the iteration. Okay. So, that is basically what is damped Newton's method, and I mean, this is a very straightforward method. I mean, there is nothing very sophisticated that is happening when you compare it with Newton's method, right. So, yeah, that is what is damped Newton's method. So, all right, yeah, that is I mean, this is this actually would take care of no global convergence issue. So, in case So, I will also tell you this. So, suppose you start at a particular point. So, note that you do not know x star. So, if you do not know x star, you will obviously start at an arbitrary point, right. So, suppose you got that because of no global convergence property, the answer actually blew up. Okay. So, let us say that actually happened. What will you do next? I mean, so suppose you started with 2 comma 2 and you do not know that 0 comma 0 is the answer. So, you do not know whether to increase the value or decrease the value, right. So, whether should you go to 3 comma 3 or 1 comma 1, and it could be that you should increase in one of the axis and decrease in the other axis. So, you may have to choose, for example, 1 comma 3, right, based on the problem. You do not know all these things, right. So, it is actually hard when the answer depends on the initial point, right. So, damp Newton's method comes to our rescue. So, you can actually use Newton's method if the answer gets to be wrong because of no global convergence property. Just move ahead to damp Newton's method, and yeah. So, the answer you will get the answer, and yeah. So, that is the other thing that I wanted to say. And one more thing about damp Newton's method is, you might also be thinking whether damp Newton's method would take care of the other issues as well. For example, if Hk inverse was not a descent direction, right, Hk inverse dk was not a descent direction, that is when Hk is not positive definite. So, would damp Newton's method take care of that? Unfortunately, that is not possible, because the issue there is not the step size, it is actually the direction, right. So, even if you choose an alpha that is less than 1, the direction still is an incorrect direction, right. So, damp Newton's method does not work if the issue occurs because of minus Hk inverse dk is not a descent direction, right. So, let me illustrate that here. Okay. So, if you recall, we had so we had this example x1 squared e power x2 plus x2 squared e power x1. When you start with minus root 2 comma minus root 2, we had an increase of the f value, right. So, and the convergence was to a saddle point, right. So, let us try the same method here to see if it actually works. Okay. So, yeah, we will just repeat these steps there as well. Yeah. So, you can see that you have a print statement, and yeah. So, here is the backtracking line search step. Okay. So, let us check what happens here. So, you can see that there is no change, right. So, oh okay. So, I did not print f of x here. So, was there a problem? Yeah. Yes. So, you can see that there is absolutely no change in what was there previously and what is happening here. Okay. So, yeah, that is I mean, just to note that damp Newton's method works for no global convergence, but yeah, I mean, it does not rectify the other properties. Okay. The method rectifies no global convergence, but does not rectify minus Hk inverse dk being an ascent direction. So, yeah, the opposite of descent direction is ascent direction. Okay. All right. So, now the question is how do you rectify minus h k inverse d k not being a descent direction, right. So, yeah, so what we do is we actually modify h k to a slightly different matrix. Okay. So, I will tell you how that works. Okay. So, I will just call that modified Newton's method, but before that I will explain the theory behind that. So, yeah, the issue as you can see is that, so if h k is not positive definite, okay, then there exists an eigenvalue lambda I that is less than or equal to 0. Okay. So, a positive definite matrix, you might have known this property by from linear algebra. If you do not, you can know it now. So, one of the way of characterizing a positive definite matrix is to say that the every eigenvalue of that matrix is positive. Okay. And for a negative definite matrix every eigenvalue is negative. For a positive semi definite matrix every eigenvalue is non negative. For a negative semi definite matrix every eigenvalue is non positive, and for an indefinite matrix there exists at least one eigenvalue which is positive and one eigenvalue which is negative. Okay. So, since it is not positive definite, that means there should be at least one eigenvalue which is non positive. Okay. So, what about modifying this matrix so that every eigenvalues are positive? Okay. That is, construct, so to modify h k to be a matrix with all positive eigenvalues, let h k hat be h k plus lambda I, okay, where lambda equal to half minus min of lambda i's. So, if lambda i's are the eigenvalues of h k, okay. So, find the minimum of those lambdas, lambda i's, okay. So, since there exists at least one eigenvalue which is non positive, right. So, you will have this min I of lambda I to be either 0 or some negative number, and lambda will be something greater than half. Okay. So, and I claim that h k hat is a positive definite matrix. Why is that? So, note that the eigenvalues of h k hat, okay. So, now the eigenvalues of h k hat, okay, are lambda plus eigenvalues of h k. Why is this the case? So, you know that so I mean the proof is just simple, it is, so if, so we have already told that lambda I are the eigenvalues of h k, right. So, we know that h k minus lambda I will be 0, right, lambda I will be 0 for all I, okay. So, yeah, this is because, or since I will write h k plus lambda I minus lambda plus lambda I into I is 0, right. So, I have just added and subtracted lambda I, okay. So, I mean both the equations are the same, and what this means is that h k plus lambda I is h k hat. So, this is just hk hat yeah minus lambda plus lambda I into I equal to 0, the determinant of this is equal to 0. So, yeah, that proves that the eigenvalues of hk hat is just lambda plus the eigenvalues of hk. Okay. And since I have written lambda equal to half minus min lambda I, so you can see that the minimum eigenvalue of hk hat is half, right, and that is positive. Okay. So, you can ask me what is the sanctity with half, right. So, you can put any positive number, that is correct. So, I mean one thing is if it is very close to 0, then inversion will actually make it too high. Okay. That is the H inverse will be, yeah, it is still invertible if let us say the lowest eigenvalue is not 0, but it is 0.00001, right, or 10 power minus 8, 10 power minus 10 or something of that sort, right. So, that means your H inverse will blow up, that is not what you want, right, and you do not want hk hat to be too high either, right, that is the lambda the value half what I have written, right. So, I mean if you put it too high, then hk and hk hat differs by too much, right. So, we want to retain the properties that are there for hk as far as possible, right. So, yeah, you do not want the delta to be too high either. Okay. So, yeah, this is what I am going to do. I am choosing lambda equal to half minus min lambda I over I, and I am instead of the descent direction being minus hk inverse dk, I am going to make it minus hk hat inverse dk. Okay. So, that is the change. So, the modified Newton's method is it is just, yeah, same initialize business, so yeah, here we will write first we will define lambda as half minus min over I lambda I, where lambda I is eigenvalue of hk, maybe I will write it as this if that is required. Okay. And yeah, x will just be x minus hk plus lambda I inverse dk. Okay. Yeah, so I will call this way. Okay. All right, and yeah, the rest is the same. So, just to put it in a nutshell, instead of minus hk inverse dk, I am going to use minus hk plus lambda I the whole inverse dk, where lambda is half minus min lambda ik. Okay. So, and I claim that this will set the issue of minus hk inverse dk be not being a descent direction. So, that is also very simple to see, because I mean the issue came because hk was not a positive definite matrix. Now, hk plus lambda ki is a positive definite matrix. So, it should help us. So, let us verify if this particular method works in this example where we were failing for a long time. Okay. So, I will take off the yeah. So, yeah, I reverse the changes that I did for damped Newton's method. So, this is plain Newton method, Now, I have to find lambda in the first place. So, yeah, that is just min of okay. So, yeah, so you might have seen np dot linalg dot eig of eig of h of x, right. So, eigvals actually I mean prints just the eigenvalues, eig prints both the eigenvalues and the eigenvectors. So, eigvals prints only the eigenvalues. Okay. So, I have called this as L, and so here okay. So, there is one other change I should have told you. So, yeah, this is okay, maybe I will have to write this again, but it is okay. Yeah, so this is true only if so this is if min I lambda I k is less than or equal to 0. Okay. Otherwise, I am just going to call this 0. Okay. That is, in case h k turns out to be positive definite by itself, I am not going to disturb the algorithm. I am going to disturb it only if h k turns out to be a matrix that is not positive definite. Okay. So, yeah, I should have written this properly. So, it is okay. So, x k plus 1 is x k minus h k plus lambda k I inverse d k, and yeah, this is k equal to k plus 1, and yeah, you output x star equal to x k. Okay. So, fine, I will do this in a very simple way. So, when L is less than or equal to 0, so you should add sorry L into np dot I of 2, okay. Sorry, L minus 5 sorry 0.5 minus L, yeah. So, it is half minus L only when L is less than or equal to 0, otherwise if L is greater than 0, this term will be 0. So, you are just left with h of x as I mean just like that. Okay. So, let us check if this corrects itself. Yeah. So, you can see I started with minus root 2 minus root 2, right, but you can see that yeah, we have converged to 0 comma 0. Okay. So, not just for this example, even for the example x naught sorry x 1 squared minus x 2 squared, right. So, without this part you can you can recall that it got converged to 0 comma 0, right, which is a saddle point. But if you implement this, you can see that it actually goes to 0 comma minus infinity. Yeah, maybe I will just do that and end this class. Okay. So, yeah, I will copy this algorithm down and yeah, just modify it to be x naught squared minus x 1 squared. So, this will be 2 x naught minus 2 x naught and minus 2 x 1, and this is much simple. It is just 2 0 0 minus 2. Okay. So, x 1 squared minus x 2 squared. So, if I just so yeah, I mean let me put this as 0 just for the sake of it, to actually show you that I mean this algorithm converges to I am sorry, I should have put 0.5. so that I am nullifying the effect. So, if it is 0.5 every time, then this is always 0. Okay. So, that is the reason. You can see that it converges to 0 comma 0, which is absurd, right, because it is a saddle point. But now, if I modify this to the modified Newton method, okay, you can see that it runs for 442 steps and says that, yeah, so x1 is 0 and x2 is minus infinity. Okay. So, yeah, I think that makes it clear how modified Newton's method gets over the issue of minus hk inverse dk not being a descent direction. It also gets across the issue that hk could be singular, right, because if hk is singular, it means at least one of the eigenvalues is 0, right. If that is the minimum eigenvalue, then again you can use this method and modify it to have all positive eigenvalues, that is non singular, and get over that issue as well. Okay. So, we will end this lecture, and in the next lecture yeah, we will look at some more properties of Newton method. Thank you.